go. Okay, so we've looked at 2 homework problems. We good to go? All right, and I'm sorry I didn't have that being recorded. So for our lecture, we're looking at the harmonic oscillator. We started with the harmonic oscillator on Wednesday. And I don't think I showed this picture. This picture is showing what the wave functions look like for the solutions we're going to find. So of course, we're not there yet, but we have different energy levels. And one thing to note here, this picture illustrates that the energy levels are even gaps, whereas for the particle in the box, they were definitely not even gaps. Also, you have the ground state energy is not at 0, it's up here at some energy. And you have symmetric and anti-symmetric solutions. It's somewhat reminiscent of the particle in the box, but it's not the same. The reason is fundamentally this is like a box with the width of the box changing based on your energy. The more energy you have, the wider the box is fundamentally. And so that's a basic difference in the way the solutions look. When we look at the equations aren't going to look alike at all. But you look at the functions and you see some similarity. Now this here, what's the importance of psi mod squared? It's the probability density. So I can look here right away and I can say, okay, if it's in the lowest state, its most probable position is right here in the center. The lowest energy state corresponds to what we're comfortable with as far as a simple harmonic oscillator. When a child's swinging on a swing, it's approximately a simple harmonic oscillator. And the child is, going to be moving between these positions, and it's somewhat reminiscent. We get to these other things, probabilities of most probable location changing around becomes more odd. So that's just looking at what the solution is. Now back to the problem. So the simple harmonic oscillator's momentum equation is 1/2 kx squared, or, and I showed you last class period, we could substitute that k is equal to m omega squared, where omega is the frequency of oscillation in radians per second, it's the angular frequency. And then we use that to make the Hamiltonian. So we have the kinetic energy operator plus potential energy operator, both acting on psi is equal to total energy psi. And then we rearrange this to say it's 1/2m p operator squared plus m omega x operator squared. What was the next step after that? Because that was where, up to here, it's kind of reasonable. What was the next step? We find 2 new operators, the raising and lowering operators as we call them. Now, raising and lowering can't mean anything to you at this point because you don't know these operators. But that's why this one has a plus sign here to go with a minus sign there. Because it turns out the one with the minus sign there is the one that's going to raise the energy state. So the names are given based on knowing what the answers are. When the idea first comes up, you don't know what they're going to do at all. It's all mathematical trickery. By the way, there are 2 ways of solving this, the mathematical tricky way and the analytical way. Today, we'll work on the mathematically tricky way. And then once we finish that, then we'll go to the analytical way. So we can see the 2 approaches and basically appreciate how mathematicians can be tricky. Now, what I want to do from this point is to consider what is A plus A minus. So if I just do that, I don't think I did this last class period, did I?
We did it, but pretending that they weren't operators.
Right, right. So there's writing it out. Now I just have it written out with operators. And now when I multiply, remembering that they're operators, the order of the operators is important. So this is equal to factor out what we can. I times I is minus 1, so minus I times plus I is plus 1. P operator squared. And then I'm going to have minus I hat M omega P operator X operator plus I hat M omega X operator P operator plus M squared omega squared X operator squared.
What is I hat?
It's a very good question. It would be a unit vector in the X direction in a different class. Whoops. All right, so what we have here then is equals 1 over 2 h bar m omega p squared plus m squared omega squared x squared plus I m omega x comma p. Notice the xp was the one with the positives. That's why I have it x comma p. But if we go back to the Hamiltonian, notice the Hamiltonian was 1 over 2m p hat squared plus m omega x hat squared. And so we can actually make the Hamiltonian from this by saying, if I take the first two terms separately, I'm going to have, and that was 2m. What page am I on? This one. Is that writing the first two terms correctly? Well, I think it's correct, but I have the 1 over 2m m omega x. Keep going too far. I put these in the wrong order. So this here is my H operator. And then I have left over plus I over 2H bar X commutator with P commutator.
How did you factor out?
I factored out the H bar omega so that I would have the 2m here because my operator, the Hamiltonian, had 1 over 2m.
Right.
And you told me, and I believe you, although I guess I could look in the front of the book just to, does the front of the book have the commutator? Yeah, X comma P is IH bar. Just making sure. So replacing that commutator with its value, I times I is minus 1, so minus 1/2. So what I have here is A plus A minus is equal to the Hamiltonian over h bar omega minus 1/2. Which gives us a value for the Hamiltonian. The Hamiltonian can be written in terms of these two operators, A plus and A minus, as
How were you able to get rid of the M omega that was in that last term, the IM omega XP commutator? The last
that was by dividing. I had Im omega here divided by 2 h bar m omega. So I canceled one of the m's, one of the omegas. I was left with I on top and 2 h bar on bottom. Now I will leave it to you to show if I do it the other way around, A minus A plus, that I will get a similar relationship so that I can have my Hamiltonian either written, this is what we just derived, or if you did it the other way around, you would have had that. Right, so this one here is the one that I showed. What do you suppose the commutator is between A minus and A plus? That's the first half of it. Everybody wants to do this one, right? Totally. Well, the things that you know are going to disappear right away. The terms that have p squared or x squared, those are going to disappear immediately because the order doesn't matter for p. If it's p and p, the order doesn't matter. If it's x and x, it doesn't matter. So I'm going to only look at the cross terms. Everything has out front 1 over 2 m omega h bar. And then looking only at the cross terms, I had m omega x hat perfect times minus I p hat plus I p hat m omega x hat. And then down here I'll have plus I p hat m omega x hat minus m omega x hat I p hat. So making things as simple as possible, notice I have m omega in the numerator in every term and I in the numerator in every term. So I'm going to factor out an I m omega. And I have minus x hat p hat plus p hat x hat plus p hat x hat minus x hat p hat. It's getting easier. Notice the, I forgot an H bar here. The m and omega are going to cancel for me. And I can combine this and this to have two of them, this and this to have two of them, so that I'll cancel the two. So it's just equal to I over H bar of p hat x hat minus x hat p hat. And p hat x hat minus x hat p hat is, if you will, minus it's just easiest to write it that way. What am I going to get here? One. It's not stupid. It's a nuisance. You totally wanted to do that, right? Notice this is instructions to me as the teacher. Check the commutator. So when you come back to this, now you can see that these two have to relate to each other because a minus a plus is equal to 1 plus a minus. Right, what we just found. So we found this one. So let's put it in here. A plus a minus is equal to a minus a plus minus 1 if I just rearrange this to solve for a plus a minus. Put that into here. And if I take a minus a plus minus 1 plus 1/2, that gives me minus 1/2. Yeah. Now I would say, so that saves us having to do the derivation again for the other order. Both of them were pretty long work, really. So what have we accomplished? Just to make, since I only have 7 minutes left in the class period, what we've accomplished is we've shown that we can write the Hamiltonian in terms of these two operators that were proposed. And these two operators, remember, are complex conjugates of each other. That is, a minus is equal to a plus star. That's also going to be important here in a minute. Now, it can be shown that if the Hamiltonian acting on a wave function is equal to the energy times a wave function, and this here is the Hamiltonian, right? Two different versions of the Hamiltonian. Then we can show that the Hamiltonian acting on a plus psi is equal to, as shown here. Well, I say it can be shown, but it's an important piece of work to show that. So H operator acting on a dagger psi sub n is equal to, and I'm writing out the H operator, and I'll just write it in the first form that's shown here. So that's going to be a plus a minus plus 1/2. Oh, I forgot the H bar omega So there's my H. My H operator, I'm going to rewrite it because that's sloppy and because I want it to be in a different color. So there's my H operator. And then for psi, I had it acting on psi plus psi n. And we want to make sure this is what I have written up above, that it can be shown that. It can be shown that this is true. So we're checking to see if that's true. Fortunately, not that bad. So here I just distributed the A dagger. Remember, the order of operators is important, so, or A dagger, A plus. So the A plus had to remain on the right-hand side. So there's the A plus. I'll keep my color coordination for the A pluses. So there you can see the A plus on the right-hand side was the one that was from my wave function. To stay complete with my color coordination. But now comes the part that's a little bit tricky. Now we strip it from the left side. So I have an A plus on the left side of both terms. And so And so if we look at what we have up here, the A minus A plus minus 1/2 A minus A plus minus 1/2 is equal to H, or so that means A minus A plus is equal to H over H bar omega times, oh, is that wrong? Plus 1/2. And so if I put that in here, boy, I feel like I made a mistake. But so what I have shown now, well, I'm one step away from completing it. The H operator acting on A plus psi sub n is equal to, these are now numbers, so I can move the operator through. Now, this here, I mean, it seems like just a bunch of algebra. I'm guessing that's what it seems like to you at least. But it does have an important quantum physics outcome. What this says is that if psi sub n is a function of the Hamiltonian, then so is A plus psi sub n. But it's a function that has an energy that's increased by h bar omega. So this A plus, now we can see why it's called a raising operator. If A plus acts on a wave function psi sub n, it will give you a new wave function of the operator. So it's a new energy state with a raised energy. Hence, it's a higher energy state, a raising operator. So what we've shown is that if psi sub n is a function of the Hamiltonian, then so is A plus psi sub n. So as soon as I find my fundamental psi sub n, the lowest energy state possible, then I can just use the raising operator and find all the rest. And likewise, I'll be able to, if I can find the energy of the ground state, I'll be able to build up all the rest of the energies. Now, I did not show, but you could see by analogy that if I do the lowering operator on psi, it's also going to give me a lower energy state. And so this lower one I did not show, I only showed the upper one. And finally for today, clearly, the energy for the raised state was E sub n plus h bar omega. So the energy of the n plus 1 state is energy of the n state plus h bar omega.
How do you sub in E sub n?
Because that was our given. Given that the Hamiltonian acting on psi sub n gives you E sub n times psi sub n. That is, the psi sub n is a function of the Hamiltonian. So we don't know what that function is. We're just saying, given that we have the solution, and we're going to use that kind of recursively then to find what the solution is. All right, I'll see you tomorrow.